Good morning, everyone. So let me kind of check in who's here. So something to be aware of is that this week, or our third exam is coming up. What's going to happen, and this will all be out in writing after class when I put an announcement together. But our third exam is going to be a real take-home one. Yeah, so everything is take-home. But what I mean is that it's going to be assigned on Friday, and it's going to be due the next Wednesday, so the last day of classes. So you'll have a good amount of time to work on it. For the exam, you will be able to ask questions of me. You're able to use your notes and the textbook and everything on Canvas, not other students. But so we don't have to spend a class period and making it this longer time. Also, it gives you a little more flexibility to kind of fit in with your lives these days, but also your classes at the end of the semester. Kind of one last check here. Okay. And so that will be all on sequences and series. So today we're going to essentially be finishing up the convergence tests part. A different view of series is the topic that'll occupy the last week. But when we make that shift, and it'll be pretty clear when that happens, the new material won't be on the exam. Right, so watch out for that. To help you with the exam, I've posted some practice materials. So we have all the lecture notes, the YouTube videos are there, and the textbook also is helpful. So I put up some, like a practice quiz, which is, here's a bunch of series, figure out what the deal is, a practice exam, quiz solutions to the last few quizzes, and also some practice quizzes on, so it's all sorts of different tests, but also this week in lab, we're doing we're going to be talking about the last few series tests, and in general, just talking a little bit about what do you do if you encounter a series. So there's some practice quizzes there. So there's a lot of stuff on here. If you have any questions, I'd be happy to talk about it. A lot of it has solutions. The practice exam doesn't. But if you want to talk about it in office hour or over email, I'll be happy to do that with you. Right, so the exam is coming up, and let's kind of get to the last of the series tests. So we really briefly introduced this last time, but now we'll really talk about it more carefully and see some examples of it in action. So we're seeing two new tests. The last two we're going to introduce, called the ratio test and the root test. They're well named because the ratio test, you look at some fraction, and the root test, there's going to be a big root showing up. So the ratio test says if you start with a series, AN, and you form this limit. So this will hopefully become more clear in examples, but what happens is The absolute value here is just always there. Largely, it says if there's an alternating part, forget about it. So we make it all positive. And then we take the terms of this series, the an on the bottom. An plus 1 is the terms of your series has some n's in it. Replace all of those with n plus 1s. So you make a fraction like this, which will have a lot of n's in it, and you check if that has a limit. If that limit exists, then there are 3 cases. If the limit you get is less than 1, that means your series converges absolutely. So recall that this converging absolutely meant not only does your series converge, but it also converges if you put absolute values on it. So if your series is alternating and you use the ratio test to get a limit, and that limit is less than 1, then you know that your series converges, and it would even converge if you didn't have the alternating part there. If L is greater than 1, then your series diverges. And if L equals 1, then that's where the test is inconclusive. This is kind of like in the test for divergence. If your limit was 0, then you just say, well, it could go either way. That's what this is saying here. If you use the ratio test and your limit is 1, then you can't say either way. So one thing that is important as you introduce the ratio test and the root test is we've had a bunch of different tests that essentially come down to compute a certain limit. So one thing you'll need to make sure that you're keeping straight is for the different tests, what limits are you computing? And then once you find that limit, what are the cases that let you draw which conclusion? So in this case, less than 1 is good, greater than 1 is bad, equals 1 means you have to do something else. We have these other tests like the limit comparison test that says if you got 1, that's fine. If anything other than 0 in the limit comparison test says that the series do the same thing. So there are a bunch of tests where you take limits, but which limits you take and what you do with those limits once you've taken them is different. So you want to make sure that you look at those and in doing examples, try to make sure that you're keeping the different tests straight. So this is good if there's a lot of multiplication, which means, or things like factorials or exponential functions. So let's see an example. So here's a series -2 to the n over n factorial. One thing which is good to do, especially for the root test, the ratio test, is instead of having a negative number raised to a power, break it into the alternating piece and a positive number raised to a power. So using an exponent rule, you can do that. And this just makes it easier because when we put absolute values on, the effect it's going to have, if you take the absolute value of this, it just kills off the alternating part because instead of bouncing between 1 and -1, it's always 1, and the other things are positive so they don't change. So if we use the ratio test, this is the limit we want. The limit of an plus 1 over an, where an is just this formula. So that's what goes on the bottom here, just the terms in our series. An plus 1 says take that formula, but everywhere there's an n, there and there in the factorial, put an n plus 1 there. And so instead of -1 raised to the n, 2 to the n, and n factorial, it's -1 raised to the n plus 1 power, 2 raised to the n plus 1 power, and n plus 1 factorial. So before we go ahead and take this limit, there's a lot of simplifying The first thing is you're taking absolute values. So these -1 to the n's, those are just always going to be 1, so we can get rid of those. With what we're left with, so those guys are gone. Then what we can focus on is we have this fraction divided by this fraction, so let's flip the denominator and multiply instead. So we have 2 to the n plus 1 over n plus 1 factorial from the top, and then n factorial over 2 to the n, the reciprocal of the bottom. Now here is where we'll start to see why lots of multiplication, meaning the factorial and the exponential, work really well with the ratio test. Because if we flip the order that we're multiplying things, so rearrange things to group the exponentials together to get 2 to the n plus 1 over 2 to the n, and then group the factorials together, and n factorial is all the numbers multiplied up to n plus 1 factorial is all the numbers multiplied up to n, and then n plus 1. So all the numbers up to n plus 1. From the fact that we're dividing, so we get the reciprocal of the terms of the series, we have the same sorts of things in both of these factors. And because everything is multiplied together, when things are multiplied, you just get to cancel whatever you want. So what gets to happen here is the 1s, the 2s, the 3s, everything up to the n's cancels. The denominator has an extra factor so that there isn't on the top. So that is going to give us 1 over n plus 1. And then here we have a bunch of powers of n, or sorry, a bunch of powers of 2. So subtracting the exponents, or canceling a 2 to the n from both of them, gets us just an extra factor of 2. So because there's a lot of multiplication after we flip and multiply, we get a ton of cancellation because we have the same sort of thing on the top and bottom. Just this factor that came from the top of our fraction has a little bit more. And those are that little bit more is what's left over after we do all this cancellation. So after canceling everything, we have 1, 2 here, and we have an n plus 1 in the denominator. And this is what we actually take the limit of. And if we take this limit, the 2 stays fixed, the denominator goes to infinity, that means this limit is 0. So then we go up and check ratio test, less than 1. 0 is less than 1, so that's okay in this case. So by the ratio test, this series converges absolutely, in fact. So not only does this sum up to a number, but if you took the absolute values, which would give you just 2 to the n over n factorial, that would also converge. Before seeing some more examples, are there questions about this series that I can clarify? So this is a kind of typical example of the ratio test. You look at this and say, powers and factorials, that's a lot of multiplication, that's really good for the ratio test. The limit you set up is the terms of the normal terms on the bottom, the terms with n plus 1s instead of n's on the top. You cancel any negative things, flip and multiply the bottom, and then pairing up the pieces which are similar, you get a lot of cancellation. After that cancellation, you can find the limit and then check what that limit means. Less than 1 is good, greater than 1 is bad, equals to 1, you aren't sure. So the ratio test is a good test. I like it. It's once you get used to it, it's pretty quick and easy to use, especially after you get a feel for how the cancellation works. But it's not perfect. In fact, it's really bad for series that look like P series. So for instance, if we look at the series n over n squared plus 1, now if you were to evaluate, or if you were to try this by another way, really the way that works is you look at this and say, well, I have an n over n squared plus 1. Let's compare that to 1 over n, canceling an n from each of those. This diverges, and I think the limit comparison test is probably your best bet. And so then this series diverges. So this is a series that we can compute where we can decide whether it converges or diverges, and it's like some problems that we've seen before. But what happens if you try the ratio test? It's our new toy and we want to take it for a spin, but in this case, it doesn't work. So what happens, we want to form this limit, the absolute value of an plus 1 over an. Everything is positive, so the absolute values don't actually do anything. But what we do is take on the bottom just the terms of the series, n over n squared plus 1. On the top, we have the terms of the series, but these two n's have n plus 1s instead. And so here, the n plus 1 is the thing being squared, not just n squared. And n plus 1 shows up on the top. So we form this limit, and like last time, we have these two fractions flip and multiply. So n plus 1, if we multiply this out, n squared plus 2n plus 2, squaring and then adding 1, and then the reciprocal of the denominator, n squared plus 1 over n. If you multiply this out, what you get is n squared plus some smaller stuff, and n cubed plus some smaller stuff, and then also n cubed plus some smaller stuff. So this limit is 1. And that's the case where the ratio test is inconclusive. You don't know if it converges or diverges, at least by that test. We can figure out by another test that this does diverge, but the ratio test won't get us there. And what will always happen is if you only have powers of n, this situation is going to happen. You're always going to get, after you flip and multiply, you're going to get the same degree on the top and bottom, and you'll always end up getting 1. So if you have just powers of n, so something which you could compare to a P series, you don't want to use the ratio test. It's not going to work. So it's a case where it does work, 4 to the n over n to the 4th. So here we do have a power of n, but it's not just powers of n. So this is one where the ratio test will get us to the answer. And like before, same limit, an plus 1 over an. Regular terms on the bottom, n plus 1s in that term on the top. Flip and multiply, and now group things together. So we have the 4 to the n's, those we want together, and the polynomials, those we want together. We want to put them together because once we are here, they're set up for exactly, well, at least in the blue case, we're set up for canceling. In the red polynomial half, we don't get any cancellation, but if you take the limit of this, you're going to get 1. they're both n to the fourth. If you multiply this out, you get n to the fourth plus a bunch of other stuff. So this limit's going to be 1. And then you can use, and this part cancels, so we'll be able to actually compute this limit. So this literally cancels to be just 4. This part doesn't cancel, but its limit is 1, so this limit is 4. And then, I made this mistake the first time I wrote this, but make sure that you're coming to the right conclusion. This 4 is greater than 1, and for the ratio test, that means the series diverges. Question about any of these examples so far? Okay. So let's see another example which really takes this lots of multiplication to heart. Okay. So let's look at this series from 1 to infinity. On the top, we have multiples of 4. On the bottom, we take 2n and find its factorial. So what this looks like, if we start writing out terms, the top is looking like 4, and then 4 times 8, and then 4 times 8, 8 times 12, and so on. So we're taking more and more multiples of 4 and multiplying them all together. On the bottom, we have for n equals 1, that's 2 factorial. On the bottom, for n equals 2, that's 4 factorial. And then we have, for n equals 3, we have 6 factorial, and then so on. So that's what these are looking like. So this is a lot of multiplication, but there are ways to have a lot of multiplication other than just n factorial. So we can deal with this with the ratio test. With a lot of multiplication, we're setting ourselves up for a lot of cancellation, but we need to be careful about what this actually looks like. So if we are setting this up, the limit is the absolute value. Everything's positive, so that won't do anything, but the n plus 1 term divided by the n term. So the denominator, so this whole thing right here, this is the fraction that we are taking the limit of. So it looks really big and gross. But there's going to be a boatload of cancellations, so it's okay. On the bottom, we have just the terms that we are adding up in our series. On the top, we have to figure out what does this look like if we use n plus 1 instead of n. So if we replace this n with n plus 1, that gets us this. We can multiply this out and say 4 times, in parentheses, n plus 1 is 4n plus 4. That's where this comes from. So we get 4 times 1 times 4 times 2, 4 times 3, and so on, 4 times n, and then 4 times n plus 1 is where this 4n plus 4 comes from. On the bottom, we're making the same sort of substitution. If we put an n plus 1 in here, that is 2 times n plus 1, this whole thing factorial. And if we multiply out the number inside to really see where do we stop, that is 2n plus 2. So so comparing these, this says, given an n, multiply all the numbers up until you get to 2 times n. This says, multiply all the numbers up until you get to 2n plus 2. So this is what our limit is. It's really big, a lot going on, but like before, we flip and multiply. So that means this goes on the bottom and 2 times n factorial goes on the top. And like before, we group these things together. Before we get to the canceling, questions about just where or how we get to this limit being the thing that we're actually going to want to compute. Okay. So now we want to think about what kind of cancellation do we get? So here it's written out for us. All the we're multiplying the same multiples of 4, but on the top we have an extra one. We have 4 times n plus 1, which isn't a factor that we get here since we stopped at 4 times n. So this 4n plus 4 is all that's left. With the factorials, first we need to think about what numbers do we actually multiply together. And so 2n factorial says multiply all the numbers together until you get to 2n. 2n plus 2 is all the numbers until you get to 2n plus 2. But how we want to do this is we want to think about what parts do these have in common. So if you're multiplying all the numbers up to 2n plus 1, you go 1 times 2 times so on until you get to 2n. That's the part that's in common with what the factorial on the top. But then there's the next number, 2n plus 1, and then the next number, 2n plus 2, which is where we actually stop here because it's 2n plus 2 factorial. So the way the cancellation happens in these factorial problems, or these factorial ratio tests, is a factorial is multiplying all the numbers up until a certain stopping point. The factorial that comes from the n plus 1 version is going to have a couple more factors. And you need to figure out what those factors actually are. In this case, both factorials get you up to 2 times n, but since this number is 2 bigger than 2n, we get these additional factors, 2n plus 1 and 2n plus 2. And written this way, we can see that what they have in common gets canceled, so the limit that we're actually wanting to take is the 4n plus 4, the extra multiple of 4 that we had there, and then these two extra numbers, 2n plus 1 and 2n plus 2. And taking this limit, what we can see, and you don't have to multiply, you can multiply this out, but also just kind of seeing what would happen is these two n's would give you an n squared. So the degree of the bottom is bigger, which means this limit is 0. So then this limit is 0. What we really care about for the ratio test is that it's less than 1. So this limit is less than 1. So this series we started with converges, and absolutely is it comes from the ratio test, but doesn't matter since our series was positive, but we know that our series converges by the ratio test. Um, Questions about these examples here? So we have these examples. The textbook has some extra examples. The ratio test is, I guess, with all of these tests, but I think the ratio test, once you can get the hang of it, um, the work is sort of um, similar in these different cases. Um, and once you're used to what that work looks like, it becomes not too bad of a problem, but it does take some getting used to. And um, getting kind of up in your head what the different conditions are for the conclusion you get to draw. So keeping it straight that the ratio test, one is inconclusive and you can make a decision on either side, as compared to some other tests um, where 0 is what you're looking for, or not 0 or 1, or things like that. So a test which is similar, at least in the conclusions you draw, but different in execution, is what's called the ratio test. Or sorry, the root test. Because rather than taking a ratio, we're going to take a root. So it looks very familiar, but what happens is we're taking the limit of something different. So given any series, and take the absolute value of the terms and take the nth root of those. Then take a limit of that sequence and see what its limit is. Then we have the same 3 cases that we did for the ratio test. If this L is less than 1, your series converges absolutely. If it's greater than 1, it diverges. If it's equal to 1, it's inconclusive. So what's nice is that the ratio and root test really come as kind of a pair. They have exactly the same cases and a sort of similar look. Just it depends on what are you doing to the terms of your series, how are you forming a sequence out of those, and then once you take the limit, you're asking the same kinds of questions. So the root test, as you might guess, is really good if your series has an nth power. Because if your series has a big nth power and you're taking a big nth root, you're going to get some cancellation. So in some cases, the root test is just the glaringly clear choice. So given this series, you're looking at this and you say, look at that big nth power right there. Okay. Overboard, but like there is no other test that you should even think about applying in this case. You look at this and say big nth power, let's hit it with a big nth root, and that's what the root test does. So you take the nth root of your series, of the terms of your series, the absolute value, which is in here, doesn't apply because we don't have any absolute values. Let me get it back in there. Okay. So we take the nth root of our terms of our series. The nth root cancels this nth power, and that's exactly why we picked this test. What we're left with is just what was being raised to the nth power, and that's what we take the limit of. Same power on the top and bottom, we take the coefficients, that's 1/2 to get a half. And so we took this limit with the nth root, we got 1/2, and from the root test, like the ratio test, if your limit is below 1, your series converges absolutely. So that's what we get to say. Our series converges, it's positive, so absolutely doesn't say a lot, but we did learn that it converges. Questions about the root test? So I'd say the root test feels less flexible than the ratio test, which I think is an accurate thing to say. But when the root test is what you want to do, it is pretty quick. So just taking the nth root, in a lot of cases, you're doing that because there's an nth power, and that cancellation gets you to a pretty easy limit fairly quickly. So let's try something a little more complicated. E to the n squared over n to the n. So here, this is a function where it's not really exponential, but we're increasing the base and the exponent at the same time. So this is like 2 squared, 3 cubed, 4 to the 4th, 5 to the 5th, and so on. And here we have e to the n squared, so the exponent is n squared. So it's e to the 1st, e to the 4th, e to the 9th, e to the 16th, and so on. Those are the terms, or the parts of the fraction that we're adding up. So in this case, we have an nth power, and here we do have a variable in the exponent. So if we take the nth root, we'll get some cancellation there too. In this case, you don't have to do this, but in some cases it's helpful. If we take the nth root, that is the same as the 1 over nth power. So that roots are just fractional exponents. And rewriting it like this helps because we can think about this more of like exponent rules. What do we do to these different exponents? So first up, we can take the nth root of the top and bottom separately. And then we multiply the exponents together. Here we have n to the n raised to the 1 over n. Those multiply to be 1. So here we're taking the nth root of n to the n, which gets us just the base n, because the exponent n cancels. On the top, this is where it is more helpful to think of them in terms of exponents rather than roots, because multiplying these together, n squared divided by n gives us just e to the n. Once we make it here, we need to take this limit, and on its own, this is an indeterminate form. This is infinity over infinity. So in this case, and in sort of every test that involves taking a limit, however you have to take the limit, you do what you got to do. In this case, infinity over infinity, we can use L'Hopital's rule. The derivative of e is just e to the n again, and the derivative of n is just 1. So, and then this is just e to the n, and that goes to infinity. So infinity definitely falls under the case of greater than 1. And so the root test, by the root test, the series diverges. What's also something to keep in mind is when you get to this stage, when you're taking a limit, this is the limit of a sequence, so you're not thinking at all about convergence tests. So you're not thinking about like tests for divergence or comparison test. This is a sequence, and you're finding its limit, and that's just a separate kind of problem. So once you decide I'm using the root test, your task is to evaluate this limit, and in evaluating a limit, convergence tests aren't just, they just aren't the right kind of thing. Convergence tests let you help or help you decide if series converge or diverge. They just don't have anything to do with, or they don't help you with sequences. So this is where the time we spent reviewing how to find limits, that's really why, because limits are an important part of these convergence tests. What is also important to see, and which kind of comes from this fact, if you take the limit as n goes to infinity of the nth root of n, you get 1. You can verify this fact by using L'Hopital's rule. There's some techniques for dealing with L'Hopital's rule and indeterminate powers. As an indeterminate power, so this is n raised to the 1 over n, and so the form of this, the base is going to infinity, the exponent's going to 0. It's not clear how that balances out. In this case, the limit turns out to be 1. So the limit of the nth root of n is 1. And in fact, more generally, the limit of the nth root of any polynomial is 1. She said the limit as n goes to infinity of the nth root of any polynomial is 1. So not just n here, but if you add n squared plus 5 and took the nth root of that, you would also get 1. So where this limit shows up is that, similar to the ratio test, if you, well, sorry, I got my examples mixed up. Yeah, so before we do this example, what this can kind of help you decide is, or what this fact will tell us is, if you try the ratio or the root test on series that look like P series, they won't work. So for instance, if we back up a little bit, not a little bit, but kind of a lot. If you try the root test on this, you're taking the nth root of the top and bottom, both go to 1, and so you'll get 1. So just like the ratio test wasn't very good for series that compare to a P series, the root test also doesn't work. So that's another drawback, or it's a case where the root test just isn't the test that you want to use. As long as we're up here, in a lot of cases, so say this case, you could also use the root test in this case, which might even be a little faster, and I'll leave you to try that out. But in a lot of cases, the root test and ratio test could both get used. Factorials really lend themselves better to the ratio test. Nth powers lend themselves better to the root test. But sometimes if you have like exponentials and polynomials, you could use either one. But this fact also is useful in just computing, or in situations or for series where you can actually draw a conclusion. So given this series, n squared over natural log of n to the n, this big nth power suggests the root test is the way you want to go. N squared, we'll have to see what happens with that. What happens is we'll use this fact. So if we try the root test, that means we're taking the nth root, which is the 1 over nth power of the terms of our series, breaking it up over the fraction and then multiplying the exponent, 1 over n times 2 is 2 over n. 1 over n and the nth power here cancel, so we just get the natural log of n on the bottom. Then what happens, and this is the kind of idea between the nth root of any polynomial is 1. When you have the exponent written this way, we can break it apart into a power to a power, but you've done the other way. So here we have n squared, that raised to the 1 over n. That is the same thing as n raised to the 1 over n, and whatever that is squared. And now when we take the limit of this, n to the 1 over n, that goes to 1, and 1 squared is 1, and the denominator goes to infinity. So that means that this limit has the form 1 over infinity, that's 0. And so we can say we took the nth root of the terms of the series, the limit of that is 0, that's less than 1, so this series converges by the root test. Questions about these problems? Any of the root test, ratio test, thoughts or concerns or things that I can clarify? So these are the last 2 tests that we're going to introduce, and kind of the place that we want to get to is similar to where we were at the end of the integration section, which is kind of developing some strategy for deciding what you do. So what the problems will look like now is, here's a series, what does it do? Decide if it converges or diverges. And we don't have the context of saying, well, we just introduced the ratio test, maybe that's what I should use. So you need some kind of mental checklist for what do you look for in a series that tells you which test to use. And I have some ideas down here, but also it depends on developing kind of a hierarchy for yourself. Are there some tests you really like, ones you don't like? And while this is a sort of multi-step checklist, part of what could also be good to do is be able to look at a series and say, I see this thing, and that tells me to use this test. That's really what some of these steps in the middle are. You don't have to go through them every time, but if you see, say, an nth power, that suggests to use the root test. And you maybe don't need to think about any other tests if you can identify that really quickly. So as some things to think about if you're involving or you're trying to decide what series do. The first thing is there are 2 really easy types of series, if it's p-series or geometric. For those, it's really look at a single number, and that will help you decide if a series converges or diverges. For p-series, it's the exponent p. For a geometric series, it's the r, the thing being raised to the power. And at this point, I should say geometric series, you can also check if they converge or diverge using the ratio test or root test. But you don't need to. It's enough to say it's geometric and the terms are, or it's 1/2 raised to the nth power, 1/2 is less than 1, the thing converges. So if you can tell it's one of these simple types of series, look at it and just be done. A next thing to check, if you aren't sure, is the test for divergence. So here, you take the limit of just the terms of the series. You don't form a ratio or a root test or compare it to anything. You just take the limit of the terms. If that's not 0 or diverges, you can say it diverges. If it's 0, you have to keep going. Then for these kind of 3 to 6, you're looking for specific aspects of your series. If it's close to a p-series or geometric series, then you can do a comparison test. If it's alternating, use the alternating series test. Like we saw today, lots of multiplication. So this is like factorials and repeated multiplication and exponential functions. Those let you use the ratio test. Nth powers or some exponential functions, you can use the root test. Those are all kind of specific aspects of the series that let you identify what the most effective convergence test might be. At that point, you're looking for just other things to do. If you can't find a good test, but you can integrate it, if you think of it as a function, try the integral test. I have this low because I don't like the integral test. If you like the integral test, you can have it higher, but I would be surprised. And also we talked about if the terms aren't positive, maybe you can take the absolute value and then do a comparison test. So we're out of time. So there are a couple examples down here, just some different types of series. I think next time we're going to keep moving and talk about the next topic. But in the lab this week, I'll close this out. In the lab, we're going to be talking about, I guess, especially making sure to focus on the new types of tests that we talked about, but also just thinking about, given a series, how do you decide what are the right kind of tests to use? So watch out for that. There's some practice materials posted to help you for the quiz and the exam that's coming up at the end of the week. I'll put all that in writing in a little bit, but other than that, if you have questions, I can stick around. If not,